The universe. It consists mostly of nearly empty, apparently unbounded space with billions of stars, some of them orbited by planets. The stars cluster together in galaxies. And the galaxies cluster together. Apparently a quiet, well-ordered place with no surprises. It's not. Stars explode, sending more energy into space than our sun will radiate in its lifetime. Tremendous gravitational fields invisibly circle dying stars, increasing their weight so that a teaspoon of material would weigh 100 tons. And there may be gravity fields called black holes, so strong that even light cannot escape, giving the appearance of nothing, pure blackness. The universe is not a quiet place, and there are surprises. But man's physical and intellectual horizons are expanding, and some of these surprises are now beginning to be understood. The universe is old, very old. Radio telescopes are picking up signals about 12 billion years old. It is big, so big that distances are measured in light years. The distance light, which moves at 186,000 miles per second, can go in 1 year. And there are stars several billion light years away. These huge distances are a help as well as a hindrance. The farther the star, the younger the image we are seeing. This helps us to piece together the history of the universe. The biggest historical question, how did the universe begin, hasn't been answered. We may never find that answer, but astronomers are slowly finding new information which may someday add up to an explanation. One of the prime sources of study and information has been the stars. Of all the stars in the universe, the closest one to us is our sun, only 9 light minutes away. By studying it, we can learn things about stars everywhere else. The sun consists of several regions. The innermost is called the core. The source of most of the sun's light and heat is called the photosphere. Above the photosphere is the chromosphere, made up of flaming outbursts of gas. The outer atmosphere of the sun is the corona. Here, the effects of dramatic turbulence occurring in the chromosphere are seen as outbursts we know as sunspots and flares. Differences in temperature between the inner layers and the surface causes the hotter inner material to rise, creating the pattern illustrated here. Currents of material caused by different temperatures are called convection currents, which are probably one source of the flaming outbursts of the sun. Here is a photograph of convection patterns in the sun's photosphere. The energy for all solar activity comes from deep in the core of the sun. There, the intense heat and pressure causes hydrogen atoms to fuse together into helium atoms, releasing vast amounts of energy. To us, the sun is a giant atomic fusion engine, radiating life to our planet through its heat and light. Scientists have calculated that there's enough fuel left in it to support us another 6 billion years. But to see ourselves as a part of the big picture, our sun is just one of over 100 billion stars in the Milky Way, and an average, middle-sized one at that. To learn more about our universe, astronomers are studying the life cycles of stars. Actually, the universe is much like a forest. In a forest, there are seedlings growing very rapidly, saplings, young but growing less rapidly, Mostly there are mature trees growing very slowly. And finally, there are dead trees, which have ended their life cycle and are returning materials to the earth which will become new trees. When you look at the universe, there too you see mostly mature stars. But just like a forest, among them are stars being born and stars dying. Present theories state that stars are born from gas, mostly hydrogen and helium, present in the universe. The process is basically simple. The gases swirl together, forming a cloud. As it grows, gravitational forces spring up, compacting the cloud and attracting more material. This is the seedling stage. Next, as more material is attracted, the greater the gravity. And the greater the gravity, the more material is attracted. Finally, the pressure in the center of the cloud causes the gases to begin to heat. This is the sapling stage. When the pressure and heat becomes so great that a nuclear fusion action starts, a mature star giving off heat and light like our sun is created. When the fuel for the nuclear fusion, hydrogen, is used up, the star begins to die, collapsing on itself. The dying star explodes, returning material to the universe to become new stars, just like in the forest. Finding the dead bodies of the universe is one of the fascinating tasks facing astronomy today. At present, we do not see the dead stars themselves. Instead, using the forest example, we can only watch for the fall and listen for the crash. Different sized stars fall in different ways. Our sun, for example, will begin its death 6 billion years from now by slowly expanding to 30 times its original size, engulfing the 4 inner planets. During this stage, the sun will be what astronomers call a red giant. At the end, it will explode, throwing some material into space. The remainder will collapse into a dense burning ember called a white dwarf, about the size of the Earth. Large stars explode even more violently when their nuclear fuel is gone. Called supernova, their huge size means more material is involved in the collapse, and astronomers aren't sure just what happens. One theory is that the tremendous gravity of the supernova crushes the remains into a dense body called a neutron star. A spoonful of material at its core would weigh 1 billion tons. A body of this density could explain another stellar curiosity, the pulsar. These are bodies which send out very regular pulses of light. If a neutron star happens to be close to a normal star, the neutron star's gravitational field attracts matter from its neighbor. Entering at the star's polar caps, this matter is heated intensely by the strong gravity, creating very bright light. If the star rotates off-center from its poles, it could cause the flashing pulse we see from Earth. As we mentioned earlier, there is evidence that some of the remains of dead stars have a gravity field so strong that not even light can escape. These are referred to as black holes. We have come a long way since Sir Isaac Newton first suggested the laws of motion and gravitation in 1686. The same unifying principles which hold our little solar system together must apply equally to the most distant galaxy. Yet some stellar events cannot be explained by the laws of physics as we understand them. Stars at the edge of the universe seem to be accelerating away from the center. Laws which govern mass and speed suggest that there may be much more matter in the universe than we are able to see. Where is the rest? The answer to this question and hundreds of others are being actively sought today. And this work may soon bear fruit, for in many ways, you are living in a golden age of astronomy. Fundamental discoveries are being made, as important as Priestley's discovery of oxygen was to chemistry, or Newton's laws of motion were to physics. Why? Because just recently, we overcame a handicap as old as astronomy, the Earth's atmosphere, which, with its haze and smog and clouds, has hindered the astronomer's view of the universe. Looking through the atmosphere from an astronomer's viewpoint is like looking through a dirty windshield in a rainstorm. Above the atmosphere is like turning on the windshield wiper. So scientists started to lift their instruments above the atmosphere. What can we gain by lifting instruments past the veil of our atmosphere? Much more than just a clear view. Stars emit energy on many different wavelengths throughout the electromagnetic spectrum. However, the atmosphere blanks out all but visible light and a small part of the radio spectrum. Until the space age, astronomers were getting only part of the story. By lifting instruments above the atmosphere, all frequencies of energy coming from stars can be observed. Major astronomy experiments have been placed on manned flights, and a series of satellites called high-energy astronomy observatories scan deep space for specific kinds of energy. As new information comes in from these experiments, we are discovering small facts which, like pieces in a jigsaw puzzle, may someday explain the origin and evolution of the universe. For the future, scientists at NASA's Marshall Space Flight Center are managing the development of a space telescope. It will be placed beyond the veil of our atmosphere, seeing objects 50 times less bright than those we can see today. The space shuttle will carry into orbit special telescopes which will record X and gamma rays and infrared radiation from deep space. Each of these new ventures may add solid new facts in our quest to answer those ancient questions. How did it all begin, and where is it going?